Hello to all our participants from around the world. My name is Arya Peruma, and today we'll be learning about how to add and multiply radicals in today's webinar. So before we get started, I would like to thank everyone for emailing me with their questions, feedback, and requests for new STEM webinar topics. And if any of you today have any questions, feedback, or requests from today's webinar, please feel free to email me. And with this, let's get started with today's webinar. So today we're going to be doing adding and multiplying radicals. So before we get into these kinds of problems, what we need to first establish is the parts of a radical, which is the first thing we're going to be learning today. So essentially, if you had this, if you had root a to the m and you had a radical that looks similar to this, I'm basically going to identify the parts of this radical for you so you're more familiar with the terminologies which will be frequently used throughout today's webinar. So this root a here is what you would call the radicand. And this m here is called the root index. And this will be really useful to know for the upcoming questions in today's webinar. So for example, the first question we're going to be doing is we're going to first be looking at adding and subtracting radicals. So adding and subtracting radicals. So the first question we'll be doing is 5 root 11 plus 3 root 11 minus 2 root 11. So before we actually jump into these problems, it's really important to keep in mind that adding and subtracting radicals is really similar to adding and subtracting with variables, in the sense that in order to add and subtract radicals, they have to be like, such as the same idea as adding and subtracting with variables. So in order for you to actually simplify this, you would actually need to make sure these radicals are like terms. And in order for the radicals to be like terms, there are two things you need to look for. One, the root index for all of these terms have to be the same, and the radicand for all these terms have to be the same as well. And as you can see, this is terminology which was covered previously. So essentially, what we have to look for is the same root index and the same radicand. So first, taking a look at the radicands for all of these, for this 5 root 11 over here, the radicand is 11, that is the number inside the root. Over here, radicand is also 11, and over here, the radicand is also 11. So we know that all the radicands are the same. And now to make sure it is indeed like term, we have to make sure the root indexes are all the same. So just to refresh your memories, the root index is that tiny number you would see over here. But in this case, you actually don't see any number. And when you don't see any number like this, it is understood that the root index is 2. So for example, if I gave you root 12, the radicand is 12, and the root index is 2, because when there is no number written here, it is understood the root index is 2. If you had 12 and you had root 3 like this, the root index is 3 and radicand is 12. And that's just important to keep in mind. So in the case of this problem, as you could see, there is really no number written here. So it is safe to understand that the root index is 2. So therefore, all of the radicands are the same for all of these terms, and so are the root indexes. So we know that they are all like terms, and we can add them up. So now, just as we would with variables, what we have to do is combine like terms now. So as you can see, we have 5 root 11, 3 root 11, and negative 2 root 11. So combining like terms here, 5 plus 3 minus 2 is 6. So we have 6, and we kind of can consider the variable as the root 11. And just as we would say, if you had 5x plus 3x minus 2x over here, as you can see, this is essentially the same idea. This just has x, and this just has in terms of root 11. And as you can see, when you add all of these, that would equal 6x. So essentially, you just add the values, and you just put that variable, which is common to all, at the end. That's essentially what I have done here for this question. And this would be your final answer. It's very simple enough once you identify the root indexes and the radicands as being the same. So now that we have done this problem, let's move on to another problem with adding radicals. So our second problem, which we'll be doing today, is 7 root 6 with the root index of 5 plus 4 root 3 with the root index of 5 minus 9 root 3 with the root index of 5 plus root 6 and a root index of 5. So just as we did for question number 1, we have to make sure that all of these are like terms in order for you to add them efficiently. So as you can see, what we did previously is we made sure that the root indexes and the radicands were all the same. So we have to do the exact same thing now. So taking a look at the root indexes for all of these terms, let's make sure they're the same. So for this 7 root 6 over here, we have root index of 5. For this 4 root 3 term, we have a root index of 5 as well. For this negative 9 root 3 term, we have a root index of 5. And finally, for this root 6 term, we have a root index of 5. So we know that all the root indexes are the same. But remember, in order for you to add and subtract variables, the root indexes have to be the same, but so do the radicands. So now let's take a look at the radicands. There's a radicand of 6 here, a radicand of 3 here, radicand of 3, and radicand of 6. So unfortunately, all of the radicands are not the same. So therefore, all 4 of these terms are not actually like terms. However, as you can see, you have 2 terms here with a radicand of 6 and another 2 terms here with a radicand of 3. So just as you would if there were x and y variables when combining like variables, what you do is now we can actually combine like terms in this case. So we have 2 terms that actually have the same root index as well as radicands, and another 2 terms that also have the same root index as well as radicands. So we can just combine those like terms. So taking a look at this would actually be 7 root 6 with root index of 5 plus root 6 root index of 5. So as you can see, I'm just combining the like terms here because both of these do have the same root indexes and they both have radicands of 6. So now I'm just going to be doing the same thing because as you can see here, you have like terms again with this 4 root 3 and negative 9 root 3 as well. So I'm just going to be taking that and also writing them together so we can combine them. So now what we can do is we can carry out our simple addition and subtraction just as we would. So as you can see, we have a 7 root 6 with root index of 5 plus root 6 with root index of 5. So if you added 7 plus 1, which is basically the coefficients of this 6 root 6 here, we have now 8 root 6 with a root index of 5. And now taking a look at this over here, we have that plus 4 root 3 minus 9 root 3 with root index of 5 for both, and they're like terms, so if we combine them, that would equal negative 5 root 3 with root index of 5. And therefore, this is our answer for this. So as you can see, this is the simplest we can get it at, as now if we try to subtract these two even further, the root indexes are the same for both, but the radicands are not the same. So therefore, we cannot really subtract and simplify this further. So therefore, this is our final answer. And just as we would if there was 8x minus 5y, this is the simplest we can get our expression. We cannot simplify it even further. So just think of it as that. Just think of it as if they are not like terms here, like terms in the sense that the radicands and indexes are the same, you cannot simplify it further. So now let's move on to one final problem using adding, subtracting radicals, and then we can move on to multiplying radicals. So in order to add and subtract radicals for these specific problems, I'm now going to introduce a new concept to you guys. And this is essentially how to simplify a radical. Simplifying radicals. So essentially, now I'm going to give you an example for simplifying radicals, and I'll work through this with you guys. So if you had root 12, for example, just root 12, as you can see, this is a radical in itself, but this is not what you would call it in its simplest form. Root 12 is not a radical in its simplest form. So in order to actually simplify radicals and make them in their simplest form, what you need to do is you need to prime factor the radicand. So prime factor a radicand. And essentially, we need to prime factor this radicand. So if you're not aware of what prime factoring is essentially breaking up a number into its prime factors. And prime factors are essentially prime numbers that when you divide 12 divided by those prime numbers, they will divide evenly. So basically, the prime numbers which you prime factor 12 with would be divisors of 12. So essentially, prime numbers are basically numbers that only have two factors, one and itself. So when you prime factor numbers, you basically need to find divisors that those divisors only have the factors of one in itself. And in order to clarify things a bit further, I'll go through this with you, and hopefully it'll make sense at the end of this. So now, as you can see, we have 12 over here. So taking a look at the prime numbers which we can divide 12 with, well, we know that we can divide 12 with 2, and that would, if we do 12 divided by 2, that equals 6. And then we can divide it by 2 again. And then 12 divided by 4 is what we have so far. That equals 3. So we divide it by 3 again, and that equals 1. So basically, if you multiplied all of these prime numbers together, it would equal 12. And that's essentially what we're trying to do here. We're just trying to prime factor the numbers and basically get all of the possible prime numbers that when we actually multiply, it would equal the original number. In other words, these are the divisors of 12 that are prime numbers. So, and as you can see, we have a 2 here, and a 3 here, and all of these are prime numbers because the only factors for all of these numbers are 1 in itself. So now using this, we can just write this and just rewrite this to make it a bit simpler. And we can just rewrite this as 2 squared times 3. So now, as you can see, we have 2 squared times 3. And just keep in mind that there's really no number written as the root index here. So we know that the root index is 2. So just to clarify things further, I'm just going to write 2 over here. So we know the root index is 2. So now what we do is now we're going to simplify this further. So now what you do after you prime factor the radicand is you need to take a look at the numbers you got when you prime factored it. And right now I have 2 squared and 3. So we know the root index is 2 also. So now pay attention to the root index. So we have 2 2s and 1 3. So we have a pair of 2s. We have a group of 2 numbers. So for every group of 2 numbers, there's one of those numbers on the outside of the radical because of the root index of 2. If the root index was 3, for every group of 3 numbers, there'd be one of those numbers on the outside of the radical. And to make things clearer, I'm just going to write this out for you guys. So the solution would be 2 root 3. And what I've essentially done here is, since I have 2 2s, a group of 2 2s, and the root index here is 2 also, what I did is for every group of 2 numbers, one of those numbers exists on the outside of the radical. And since we only have 1 3, we just keep the 3 as is, and we just write the 3 inside the radical. And as you can see, this root 3 inside this radicand here cannot be simplified any further. So this works. I'll go over another example of simplifying radicals with you as well. If you had, for example, root 24 and the root index was 3, what we do is essentially do the exact same thing. We're just going to be prime factoring this again. So prime factoring this, we have 2 times 2 times 2 times 3. This is the prime factorization of 24. And now essentially what we're going to do is we're just going to write it even simpler. So I'm just going to write it as 2 cubed. And there is a root index of 3 here. So 2 cubed times 3. So now, as you can see, the prime factorization is now 2 cubed times 3, and we have a root index of 3. So pay attention to the values you got when you prime factored, and also pay attention to the root index. So we have 3 2s and 1 3. So since we have a group of 3 numbers, and we have the root index of 3, for every group of 3 of the same number, one of those numbers exists on the outside of the radical. So now if we write this, it would be 2 root 3 also would be the simplification of this, because we had a group of 3 2s and we had the root index of 3. So for every 3 of those numbers, we'd actually put 1 on the outside. So now that we've simplified this, I think we can move on to our next problem, which will utilize some of these concepts. So now, moving on to question number 3, we have 5 root 45 plus 6 root 18 minus 2 root 98 plus root 20. So as you can see here, what we have is these 4 values here. And remember, just as we did previously, we have to make sure 2 things are the same in order for you to be able to add and subtract these radicals. So first we have to make sure if the root index is the same for all of them. And yes, the root index is the same. The root index is common. They all have a root index of 2. And now we have to take a look at the actual radicals here, the radicands. And as you can see, all of them are different. So they are all not like terms. Just as we did with question number 2, we can't just combine some like terms because all of them are not like terms at this exact moment because the radicands are all different. So now, using this, we're going to use our principle of simplifying radicals, which I just previously covered. And using that, we're going to simplify these radicals further so we can make them like terms. So remember, we're going to be simplifying radicals here. So now we're going to simplify our first radical. So our first radical is 5 root 45. And remember, to simplify first, we need to break down the radicand. So breaking down the radicand, we have 45, and prime factorization of 45 is 3 squared times 5, because these are the prime number divisors that will divide evenly into 45. So essentially, these are 3 squared times 5, and also keep in mind, if you multiply these, that would equal 45, and these are all prime numbers. So this is the prime factorization. Next, we're going to be prime factorization. We're going to find the prime factorization of 18. So taking a look at this, we're going to essentially prime factor 18 here. And prime factoring 18, we have 18 as 3 squared times 2. And now prime factorization of 98 is essentially 7 squared times 2. And finally, the prime factorization of 20 is 2 squared times 5. And just keep in mind, with practice, these prime factorizations will come easily to you. Essentially, the main idea, as I mentioned previously, is essentially just taking a look at prime numbers. Prime numbers are numbers that only have the divisors of 1 and itself, and are only divisible by 1 and itself. And basically, using those numbers, we need to break down this number inside the radical into those numbers. So essentially, that's what we're going to be doing right now. So right now, what we're going to do is now taking a look at this 3 squared times 5, we have to remember that taking a look at our root index here now, so we know their root index is 2 since there's really nothing written here. We just know the root index is 2. And now we have 3 squared times 5. So we have a group of 2 3's here. And now we have a group of 2 3's. So that 3 will belong on the outside of the radical. Since we already have a 5 on the outside of the radical, that gets multiplied with a 5. And all we have left is a 5 inside. Now taking a look at this second term, we have 6 and we have 2 3's and 1 2. We have a group of 2 3's, and for every group of 2, one of those numbers will coexist on the outside of the radical. So we have 2 3's, root index is 2. So we know that 3 is on the outside of the radical, and that is root 2 left on the inside of the radical. There's only a 2 left on the inside of the radical. So now what we're going to do is take a look at this one. We have 2 root 7 squared times 2. We have 2 7's, 1 2. The root index is 2. So for every group of 2, as I mentioned previously, that number will coexist on the outside of the radical. So we have minus 2, and that is going to be multiplied by 7 because there are 2 7's. And since there's only 1 2, that just remains on the inside of the radical. And finally, we have 2 squared times 5. And now, as you can see, we have 2 squared and 5. We have 2 2's, 1 5. The root index is 2. So we know that for every group of 2, 1 will coexist on the outside of the radical. And we have 2 2's. So I'm just going to write 2 on the outside. And we have just 1 5 remaining on the inside. So now we can simplify the outside of all these radicals even further. So now we have 5 times 3 on the outside, that is 15, root 5, plus 6 times 3 on the outside. We have 6 times 3 as 18, root 2, minus 2 times 7. 2 times 7 is 14, and just root 2 on the inside. And then we just simply have 2 root 5 here. So now, if you remembered our second problem, which we did, what we did is we're essentially going to be combining like terms here. So we know all the root indexes are the same, but the radicands are not all the same. We have 2 terms that have the radicand of 5 and 2 other terms that have the radicand of 2. So what we're going to do is we're going to actually combine like terms here. So combining like terms, we have 15 root 5 plus 2 root 5 plus 18 root 2 minus 14 root 2. And essentially all I've done here is we know that the root indexes for all of these are the same, but in order for you to simplify, the radicands also have to be the same. So these 2 meet that criteria, and so do these 2. So we'll just combine like terms. So now, looking at this, we have 15 root 5 plus 2 root 5, that is 17 root 5. And that is added with 18 root 2 minus 14 root 2. So that is positive 4 root 2. And therefore, this is our final answer. And using the properties and principles and ideas of simplifying radicals, even when the radicands were not all the same at first, we've actually used that idea to actually make all the radicands the same at the end, so then we could simplify it. So now we're done with adding and subtracting radicals, and now let's move on to multiplying radicals. So the idea of multiplying radicals is actually very, very easy and quite simple. So essentially, if we had negative 5 root 14 times 4 root 6, what we could do here is we should multiply these radicals. So there's a multiplication sign between them. So this idea is very, very different from adding and subtracting radicals. And it is actually quite simpler than adding and subtracting radicals because of the fact that, as you remembered before, with adding and subtracting radicals, in order for you to combine them, the radicands and root indexes have to be the same. But for multiplying radicals, the only thing that needs to be the same is the root index, but the radicands do not have to be the same. So I'll just write that out here. So only root indexes have to be the same. Radicands do not have to be the same. Do not have to be the same. So essentially, what we can do here in multiplying radicals, all you essentially do is take your two values on the outside of your radical and you multiply those. So that's -5 times 4. And then taking a look at the inside of the radical, you multiply the values on the inside of the radical. So 14 times 6. So just taking the values on the outside of the radical, and then on the inside of the radical, you multiply the values that were on the inside of the radical for both. And now just evaluate it. So you know that -5 times 4 is essentially -20, and that is root 14 times 6. 14 times 6 is 84. So this is our answer. However, we can actually simplify this further. So I'm just going to go ahead and prime factor the radicand here. And now we have -20 root, and now prime factoring 84, the prime factorization of 84 is 2 squared times 3 times 7. And now, as you can see, the root index is 2 because there is no visible root index written here. The root index is 2, so what we know is for every group of two numbers, one of those numbers will coexist on the outside of the radical. So we have two 2's, 1 3, 1 7. Since we have two 2's and the root index is 2, we have 1 2 on the outside. And now we have only 3 times 7 left on the inside. So now if we simplify this, we have -20 times 2 on the outside of the radical, and that is -40. And inside of the radical, we have 3 times 7. 3 times 7 is 21. So therefore, this is our solution to this question. And now we're going to be doing one more multiplying radicals problem. And this will essentially utilize the distributive property, which is something I'm sure most of you are familiar with. So essentially, what we're going to do is now what I'm going to do is I'm going to give you this question. So we have 7 root 6 times 3 root 10 minus 5 root 15. So as you can see, this is another multiplying radicals problem, and this is utilizing distributive property. So essentially, I'm sure most of you are familiar with the distributive property, but if you're not, no worries, just to refresh your memory. It is basically when there is a term on the outside of the brackets and there are numerous terms on the inside of the brackets, and you take the term on the outside and you multiply out. You multiply that term on the outside with each term on the inside of the brackets. So essentially, in order to evaluate for this question, we are going to be doing 7 root 6 times 3 root 10 times 7 root 6 minus times 7 root 6 minus 5 root 15. So essentially, we're going to be multiplying these two as well. So if you multiply these two, it would come to this. Essentially, I've just written a negative here because we know that the answer to this 7 root 6 times -5 root 15 would be negative because there is a negative here. And a negative number times a positive number is a negative number. So now these individual problems kind of look like what we did previously with multiplying radicals. So we're just going to go ahead and conduct the simple multiplication of radicals. So in order to multiply, we know that we have the two values on the outside of the radicals. We have 7 and 3, so multiplying those, 7 times 3. And the root, inside of the root, we have 6 and 10, so we have to multiply 6 and 10 as well. And now, taking a look at this, that is subtracted by 7 root 6 times -5 root 15, so that's basically what we're evaluating now. And now we have 7 root 6 times 5 root 15 here. And now carrying out the same process of multiplying these radicals, we have 7 times 5, which is 35. We can write that in our next step. And now we have 6 times 15 on the inside of our radical. So we have this on the inside of our radical now. And now we can evaluate. So we have on the outside over here, we have 21, and 6 times 10 on the inside of the radical is 60. And now we have on the outside over here, 7 times 5. 7 times 5 is 35. And over here on the inside of the radical, we have 6 times 15. 6 times 15 is 90. So we have these. So now, as you can see, we have this expression here. This is what we've evaluated to so far. However, as you can see, they are not like terms. So the root indexes are indeed the same. They both have a root index of 2, but the radicands are not the same. And if you remembered from our adding and subtracting radicals, this is where the ideas of adding, subtracting radicals would come in. So after we've multiplied them, we can now see that it's actually turned into an addition/subtraction of radicals question. So now the radicands are different, but now we can use the idea of simplifying radicals to get them to their simplest forms and then see if we can combine them further after that. So now getting them into the simplest forms, what we do is we prime factor the radicand. So prime factoring 60, the prime factorization of 60 is 2 squared times 3 times 5. And now we have to prime factorize the 90 inside as well. And now prime factoring that, we have prime factorization as 2 times 3 squared times 5. So now what we can do is now simplifying. We know that the root index for all of these is kind of 2. Nothing's written here as a root index, so it is good to know that the root index is 2. And now looking at this, we have 2 2s, 1 3, 1 5. Since we have 2 2s for every group of 2 of the same number, one of those numbers will coexist on the outside. So now on the outside, we have 2. It's multiplied by 2 on the outside. And on the inside of the radical, we have 3 times 5 left over. And now, taking a look at this as well, we have 1 2, 2 3s, 1 5. So since we have 2 3s, we know that there are 2 of those same numbers, so we can bring 1 3 on the outside. So for every 2, there is 1 on the outside. So now all that's left over here is that 1 2 and 1 5, which we couldn't really make any pairs with. And now what we're going to do is we're going to be simplifying. So on the outside of this radical expression here, we have 21 times 2. 21 times 2 is 42. And on the inside of the radical, we have 3 times 5. 3 times 5 is essentially 15. And now we have 35 times 3 on the outside. 35 times 3 is 105. And on the inside of the radical, we have 2 times 10. 2 times 10 is 2 times 5, sorry. 2 times 5 is 10. So essentially, what we're going to be doing is now taking a look at this. As you can see, the root indexes are the same, but the radicands are not the same. And we cannot actually simplify the radicands any further because if we prime factor these, they would not make enough groups in terms of the root index for you to be able to simplify. So this is our final answer. This is the most we can actually combine these, and the most we can simplify this down. So therefore, this was kind of like an example of how you would integrate the adding and subtracting of radicals with the multiplying radicals as well as the simplification of radicals. So now with this, we have actually come to an end of today's webinar. So I would just like to once again thank all our participants from around the world for attending today's webinar. I hope you enjoyed. And once again, if you had any questions, feel free to email me. My next webinar will be held next week on the topic of simplifying rational expressions. And I will also be conducting live coding webinars as well the week following that. So if you are interested and you would like to sign up for any of those upcoming webinars, please check out our website and how to register for that. In addition, I would just like to once again thank everyone so much for attending today's webinar. I hope you learned something and was able to take away something useful as well. And I hope to see you all again in a future webinar. Thank you and bye.